We can extend this theorem to figure out how to find roots. Instead of just raising our z to an integer power, we can raise it to fractional powers, because we have the fundamental theorem of algebra, which tells us that a polynomial equation with degree n has n solutions within C. Remember, C is the set of complex numbers. So if we extend this to complex numbers, we can show that any complex number may have n roots. So definition of an nth root of a complex number: the complex number u equal a plus bi is an nth root of the complex number z, which is u to the n, which is a plus bi to the n. So we're going to kind of keep that in mind and use a similar property to figure out how to find nth roots. So for a positive integer n, the complex number z, in trigonometric form, r cosine theta plus I sine theta, has exactly n distinct nth roots given by this equation. Okay, so we have the nth root of r multiplied by cosine theta plus 2 pi k over n plus I sine theta plus 2 pi k over n, where k is an integer starting with 0, going all the way up to n minus 1. Let's try an example. Let's find the fourth roots of 16. Represent the roots graphically and write each of the roots in standard form. We know z is 16 plus 0i. To write this in trigonometric form, that's 16 times cosine 0 plus I sine 0. How did I know that? Well, one way is I can just think about, I want cosine 0 because I want the a to be 16. I want 16 times something to be 16. So this has to be 1. And I want the I part to be gone, so I need this part to be 0. You could also find your argument the way we did before. Tangent theta is b over a, so b over a. So we're asking, well, where is tangent theta 0? Well, that's where sine theta is 0 and theta is 0. Okay, so here's our complex number. The fourth root of 16 times cosine 0 plus 2 pi k over 4, because it's fourth root, plus I times sine of 0 plus 2 pi k over 4. Let's clean this up first. We get 2 cosine, okay, well 0 plus 2 pi k is just 2 pi k, so we'll end up with 2 pi k over 4, so that's cosine times pi k over 2 plus I sine pi k over 2. Starting when k is 0, we get 2 and cosine 0 plus I sine 0, which is 2 times 1 plus 0i, which is just 2. And now k can also be 1, so we get 2 times cosine. If you plug a 1 in here, you get pi over 2 plus I sine pi over 2, which is 2 cosine of pi over 0. Sine of pi over 2 is 1, so we get, what, 2i? K is 2, we get 2 cosine. Okay, then we're going to put 2 in here. 2 pi over 2, we get a pi. So 2 cosine pi, so that's 2 times negative 1. Sine pi is 0, so we end up with negative 2. K equals 3. We stick a 3 in here for k, we get cosine 3 pi over 2 plus I sine 3 pi over 2. We get 2 times what? 0 plus, well actually plus negative I. So we get negative 2i. So the directions said to represent the roots graphically and write each in standard form. Okay, so the standard form part is our a plus bi form, so 2, 2i, negative 2, and negative 2i. Let's represent them graphically. So draw my real axis and my imaginary axis. I'm going to plot 2 in each direction. Here, 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 and here, because this is 2, this is 2i, This is negative 2, and this is negative 2i. Now we're going to find all cube roots of 8 times negative 1/2 plus root 3 over 2i. A is 8 times negative 1/2, which is negative 4. B is 8 times root 3 over 2, so what's that, 4 root 3? And our r value is taking a squared plus b squared and putting it under a root, so negative 4 squared plus 4 root 3 squared, all under a root, so that's what, 16 plus. Okay, I get 16 plus 16 times 3, 48. So what is that, square root of 64, which we know that's 8. And I can find the argument, put b over a, and I get what, negative root 3? And tangent is equal to negative root 3. I can think about this as negative root 3 over 2 and positive 1/2. I know it goes sine over cosine. So 1/2 square root of 3 over 2. I know that's some multiple of pi over 3. What quadrant am I in? So it looks like my real, imaginary, looks like my real part is negative and my imaginary part is positive, so I'm in this quadrant. I know I'm going to use, what, 2 pi over 3? So let's rewrite z in terms of its trigonometric form. Z equal 8 cosine 2 pi over 3 plus I sine 2 pi over 3. So if I want the cube root of z, I can write the k forms. I'll get the cube root of 8, and I'll get cosine 2 pi over 3 plus 2 pi k over 3. And the 3 is because it's a cube root. And then I sine 2 pi over 3 plus 2 pi k over 3. What happens when k is 0? The cube root, z sub 0, I get what, 2. Okay, then cosine, looks like 2 pi over 9, because I 0 here, so I get 2 pi over 3 divided by 3, plus I sine 2 pi over 9. If k is 1, I get 2 times cosine, okay, I'll have 2 pi over 3 plus 6 pi over 3, that's 8 pi over 3, so 8 pi over 9. And then if k is 2, and I go up to 2 because I have a cube root, I go 1 less, so I end up with cosine. So if I put a 2 in here, I get 2 pi times 2, I get 4 pi. So 4 pi is 12 pi over 3, so I have 12 pi over 3 plus 2 more pi over 3, so I have 14 pi over 3, and then I divide that by 3, so I get 14 pi over 9 plus I sine 14 pi over 9. And you can also plug these in a calculator and figure out your decimal approximations if you want to, but here they are. Cube roots of that complex number.